Let's recap what we have seen in the previous session about variational autoencoders. We start by this concept that assume we are given a data set of faces. We are given a data set of images of faces. For example, we have 60,000 images. If you want to assume a face image, you may consider different type of images. It means that assume a machine is instead of you. The machine must model a very complex probability density so that it can model the general types of faces. The distribution itself may be very complicated, okay? But assume that some other information are also for the current point. Assume that some other information are also given, and that other information is the high level or abstract representation of the faces. For example, instead of the faces, some properties are also given. For example, the pose, the gender, and also other properties that you can imagine for a face. So if you have access to those properties, it means that you can better imagine faces with that types of properties. It means that the distribution becomes much simpler. This is exactly what we follow in the variational autoencoder. But the most important point is that the data set is just the images, and this high-level information is not given. So how we treat them? We assume that they are a random variable, which are not visible or observed, or equivalently, we call them latent variable, hidden variable. Okay, this is the overview for the variational autoencoders. We see that in the case of variational autoencoders, they have a very well correspondence with GMMs in this image. As you can see, in the case of GMM, we assume that the thing which is not observed is itself a simple random variable. A discrete random variable is a categorical random variable. It means that we just have some categories of data. It can be worked, for example, for iris data set where the distribution is itself simple. Iris data set, I mean the set of this property is not the image of iris. Petal length versus petal width. For this case, it works, the GMM, but maybe for the case of iris images, it does not work, and we need the variational autoencoder. But when we go to the more complex data set, we need to add, let's say, capacity to this latent variable. So we go to the continuous word with a Gaussian generally random vector. And also, again, here, we assume that given the latent, which is not observed, which is not given to us with data set, the distribution over what we observed is very simple. This stage is exactly similar to GMM, just with one minor change, that in GMM, the latent variable plays the role of just a selector. You mean for different categories, you have two parameters. One is the mean, and the other one is the covariance matrix. For example, the last one is 3. And the latent just is a selector, say that which of those distribution is selected. But in the case of variational autoencoders, the role is much more complex. It means that the latents go through two neural networks, and then in the output of those neural networks, you generate the mean and the covariance matrix for your conditional distribution. This is the difference between GMM and variational autoencoders. And you can see that you can easily fit a GMM using a variational learning method. If you previously see GMM in your previous courses, you may fit them using expectation maximization, which is another app, which is really correlated with the variational learning, and we see that expectation maximization is a special case of variational learning. Any question? So we start with the let's say with the generation, and we see that if you have a trained model, you can easily generate data using the procedure we assumed, a latent and then a conditional, and we can easily generate samples using a trained model. Here we assume that the model is trained. I sample from the latent. The latent is, for example, a Gaussian noise. I sample from that. I have a lowercase z, which is a realized vector. I give this realized vector to two different networks that generate the mean and the covariance matrix. Then I have a new Gaussian distribution. I sample from that distribution. I have a sample of my observed data. We see the challenges, and we start by the fact that to train this model, we need to calculate the probability for observed data. Why? Because as you may remember, for the autoregressive models, for the training them, we just minimize the summation of negative log likelihood for different samples of the training set. So for the training, we need the likelihood. We need to estimate the density. So we start by observing that the density is very complicated to be calculated in a closed form. As you can see, this integral cannot be solved, and you cannot have the result in a closed form. So we need some ideas to solve this problem, and this is the first challenge. The first challenge is that you cannot calculate the density, so you cannot train them. And we want to solve this challenge. So we see that the marginal, unconditional, the distribution density is an integral, and if we use the chain rule, we can see that this joint can be factorized with these two factors, and this is the definition of expectation. This is the definition of expectation of this function p theta of x given z with respect to the random variable z coming from the prior latent distribution, and I write it here. So if I can calculate this expectation in the exact form, I have the exact density. And then I can train the model. Assume that I can calculate this expectation in exact form as a function of the parameter of the model. So I have this factor as a function of the model parameter. So I maximize it, minimize it, so I can train the model. Everything will be solved. But calculating this expectation in the closed form is equivalent to calculating the integral, so it is not tractable. But we can estimate it. How? Exactly, by Monte Carlo estimation. Monte Carlo estimation says that if you have an expectation with respect to a distribution of a function, you can sample from that distribution and then calculate your function and then average over all resulting values. So I have the first step. At the first step, I use an approximation. So I approximate the probability of the data using this summation. And it can be easily calculated because based on your resources, you can select k, and then you can calculate this approximation to the true expectation, which is your likelihood. So if I can calculate this summation as a function of model parameters, I assume I call it f prime. So again, I minimize f prime of theta over the whole data set so I can train. It seems that the problems are being solved. But there is one major problem here that comes from your limited resource. It means that you cannot select arbitrary k. You cannot select large k because your resources is limited and training will be very hard. The problem is that this approximation is unbiased. Why? Because Monte Carlo estimation is an unbiased estimation. This comes from the property of MCE, Monte Carlo estimation. But the problem is that it exhibits significant variance. It is very important to understand why it exhibits significant variance. So for the current point, assume that instead of fitting a complex model, I want to fit a GMM. We said that they are exactly the same. GMM is a simplified version of what we think of variational autoencoder. The changes is that the latent instead of Gaussian is categorical, and the way you generate the conditional is just by selecting a subset, selecting mean and covariance matrix. So they are exactly the same. It means that if you have a problem here, it means that the variational autoencoders have the same problem. So assuming in the GMM, I want to calculate the density for this point. This is a point in the space. I want to calculate the density in this point as a function of model parameters. Here, for simplicity, I assume I have the model. I have a trained model, assume. I want to, for a trained model, calculate the density for this point. You can see here that I calculate the conditional for 4 different points. What does it mean? I sample from categorical distribution with parameter pi. This is instead of calculating from a normal, because I am in the GMM, I calculate from a categorical distribution pi. Okay, and the resulting categories are these 4 categories. Each of the groups show a category. You know, this is the first category, second category, third, and the fourth. So these 4 categories are selected. You should sample Z in the variational autoencoder. You should sample Z from the prior latent distribution. You know, in the case of GMM, we should sample Z from a categorical distribution with this parameter. So I sample from it, and I select K equal to 4. I want to estimate the PDF, the density, using 4 samples. It means that in Monte Carlo summation, I have 4 terms. 1, 2, 3, 4. Okay. So assume that for the green one. For the green one, because it is near to your observed data, the conditional distribution will give you a high value. Why? Because you are near the mean, and it has a covariance matrix, and to some extent, this point in the field of that covariance matrix. It is not very far from the mean of this Gaussian. So the conditional for the green point is almost a large value. This is a large value. But when you go to the other ones, which are far from the observed data, from the intended data to be calculated, the PDF here, you see that the value of the conditional probability is very small, and for the case of this yellow one, it is almost 0. So how can I calculate the probability of this point? I should average all of these 4 numbers, and the result is this number. So I calculate the density in this black circle. Any problem? In the general case, for GMM, we can exactly calculate the density. Why? Because the number of Z is limited. You can take a summation over 25 different categories. You know, for the GMM, for the case of GMM, the model distribution over the joint is a categorical times a normal with mean coming from the categorical and the covariance matrix coming from the categorical. So if you want to calculate the model for a point, it's just needed to marginalize out the random variable Z. Here is discrete, so instead of the integral, I have the summation. It means that it just needed to have a summation over 25 different points, and that works, okay? But the problem here is that we want to understand what happened in the variational autoencoder, so we use Monte Carlo estimation instead. So you see here that the resulting value for the probability of this point is the value you can see here, and I write it in the caption, okay? Again, I go to another step, and I want to again sample from the prior and calculate the density in this point. Again, I calculate it, and the resulting is this number. You see that in this case, these 4 categories are selected, and because all of them are far from your point, almost all of the resulting conditional probabilities are 0. So the result is also 0. Okay? Again, I write it here in the caption, the second, the third, and the fourth. I calculate the density of the same point 4 times. And the resulting probabilities are these numbers. What is the problem? Oh, this is not correct, you see? This is not correct. The correct number is this number, minus. Okay? What is the problem with these numbers? They have a high variance. 3 of them is almost 0, and 1 of them is a large value. So they have high variance. And maybe if you are not lucky and you do not have this number, you have 0. This is a more major problem. You know? Let's return to the variational autoencoder. I want to calculate your model probability assigned to an image. So we see that we cannot calculate it using, let's say, the integral. So I need to use Monte Carlo estimation. I need to use this summation instead. Now assume that you sample from the latent. How probable it is that the sample you get from the latent give high probability to your observed face image? How probable you randomly select one point in the latent, and when the model give high probability to your observed data, when they are corresponding, it means that what you observe, what you sample from the latent is exactly the high-level description of your image. You know, there is a correspondence between them. If, for example, you sample from pose 1, if the true latent for this X is pose 1, gender, for example, 3, age 4, how probable it is that when you sample from the latent, you exactly have the same set of high-level representation? It is very low. The probability is very low, you know, because this is the case. This is a 2-dimensional case. In the general, you have m-dimensional, and in that m-dimensional, you should be so lucky that one sample of your sampling process is exactly corresponding to the data you have at hand, X, you know. So generally this value is 0. And you average over zeros, so you have 0. This is the problem, you know. What happened, Monte Carlo should work. Yeah, it can work. But when your k value is go to infinity, and it is not applicable. This is a simple case. You have just 25 options, and you select 4 of them. So in this very simple, you are lucky, and in your first hit, you have a good option because one of them is almost corresponding. It means that this black circle is probable to come from this class, from this group. Okay? But in the general case, you are in the space of M, dimensional M. So you should select in that dimension a point which is corresponding to, for example, 1000 by 1000 image. It is very unlikely to happen. You should think of it more and more because it is not a very easily understandable point. But we work through the presentation. Yes?
Is that way to use like heuristics during sampling?
What?
To use heuristics during the sampling?
Yeah, we know that how we can update our sampling so that this problem can be solved.
Also, so that's a thing.
Yeah, that's exactly the thing. We may have some heuristic to sample better. At this point, we are stuck. Why? Because when we use Monte Carlo estimation, we see that we get zeros in one side, or we have high variance. And none of them can work. Let me see what's the... this is a great example about the why we have high variance. In the real world, assume that, again, for the simplification, just for simplification, assume that instead of the continuous latent, we have a discrete latent, where we have 10 different poses, 10 different genders, and 10 different ages. Okay, so in total, I have 1,000 categories in my latent. And then, based on those categories, when I select one sample from the category, from the latent, it means that I have one pose, one value for pose, one value for gender, and one value for age. Then, condition on that, I generate an image. Okay? Now, assume that I want to estimate the model density for a point, and the true latent is z bar. I want to estimate the probability for x bar, and the true latent is z bar. And I take 10 samples. For the Monte Carlo estimation for this k, I select 10. What happened? If z is inside the set that I select, inside those 10, it means that one of the terms in this summation is large, and 9 other terms are almost 0. Why? Because they are not corresponding to your image. They are different from your image. So the conditional distribution, this means that, assume that you say that you know that the image X is the image of a child. For example, his or her age is 4, but Z is selected such that the age is 90. It is the probability is very low, so this value is 0. Okay, what is the probability that you hit Z for this simple example? It's 0.01. With this probability, one of the samples you selected for your Monte Carlo estimation give high probability, and so the summation would be more than 0 because one of the terms is more than 0. So the summation, which is an average over all of them, is more than 0. But with this probability, you almost get 0 because what you select is not corresponding to the image you observe. Okay. So this is a high variance. It cannot be worked in practice, this approach. So the first challenge was that we cannot calculate the likelihood, and we need the likelihood to train the model. The solution was that we can cast the likelihood as an expectation and then calculate that expectation using estimated using Monte Carlo. But we have another challenge. The next challenge is that estimating the likelihood using prior distribution. It means here. You know, we are estimating the likelihood using the prior distribution. Give you high variance. So this is the challenge number 2, and we should solve it. What's your idea? How can we solve this challenge? Can we design a better sampling distribution other than the, let's say, prior? Take a look at this image here. I know that the black spot, the black circle, is my point. What are better points to sample from?
Sample from a Gaussian centered on X.
You should give me a distribution over the Z, because I want to sample Z. You should give me a distribution over Z. And he said that this distribution over Z is a better option, because I want to sample from Z. Give me a distribution over Z. Here Z is discrete. So you should give a categorical distribution. What is that category? What is your idea about that category? Exactly. Assume that I know that this is my point. So I can update my belief about Z. I can update my belief about Z from the prior to posterior. And which posterior? Let's see what we have here. The idea is important sampling. It is a very, very, very well-known approach in statistics, and you see a very simple case here, but it has lots of applications. You know, the problem is this. Assume we are in the one-dimensional space. The probability, the prior is this curve, but the function you want to estimate, you want to calculate the expectation with respect to data coming from this prior is here. It means that when you are sampling from high probability region of your prior, your function is 0. And with a low probability, you sample from the places where your function is non-zero. So they do not overlap, and the resulting is either high variance if you select from this point, or 0 if you select from high probability regions. Is it clear? Yes.
What was the small curve?
This small curve is what we want to calculate the expectation. For example, is f of z, and you want to calculate the expectation of f of z for samples coming from p theta of z. This is the expectation. This is instead of p of x given z. The model, assume that this is the curve of your conditional likelihood. Clear? They are not overlapped. In other words, you are not triggering your functions in the right place. If you trigger the function in the region where the function is non-zero, but because of your density, the density you are calculating the expectation, you are triggering the places where your function is 0, you always get 0, so you have 0 average. And you cannot uncover the properties of your function. You know? So the solution is something like this. You sample from something like this, and then apply some corrections. First, trigger the function in the right way and calculate, for example, the mean, and then have some correction values so that you can retrieve the original things you want. This is what important samplings intended to do. Okay? So what is the framework? We want this integral. We know that this is we marginalize out z. So I can easily multiply and divide the integrand using a QZ distribution. This is a new distribution. Assume that this is this blue curve, a new distribution. Okay? What happened? This is exactly the definition of an expectation. Why? Because a PDF, a function of Z. So you have exactly the definition of an expectation. Expectation of this function with respect to Z coming from Q of Z. So we change the distribution we are sampling from. It is not P theta of Z anymore. Is it clear how we convert? So, if we are intelligent enough and we can design this Q so that the situation I represented here happened, we may be lucky to calculate the density. So the idea is to calculate this expectation. Okay, Q can be arbitrary distribution over Z. And then I start sampling from Q of Z, again Monte Carlo estimation, again averaging some numbers, and this is also again an unbiased estimation for the true the density value at point X. So we are hopefully designing Q such that the variance is decreased. Sorry. But the challenge is that how you design Q of Z. How to design Q of Z. What is the suitable QZ? Okay, and you know that if you can assume that I want to optimize with respect to Q of Z. Then other question is that optimizing with respect to a function may be not a trivial task. Yes? Okay. In this slide, we want to think of a suitable Q of Z just intuitively. We do not want to say anything about the general case, just intuitively. And in the case of the GMM, assume that I calculate P theta of Z given X. For the case of the GMM, this value can be easily calculated. Why? Write down the formulation. P theta of Z given X equals Px and the most important point about the GMM is that this denominator can be calculated easily using marginalizing out the random variable Z. If you have any problem with this notation, with these relations, come after the class, we can talk about them more. But we can calculate the posterior over the categories for the GMM easily. So this is using the chain rule, I can write it as, and all of them are clear because the prior over Z, as we have a model, okay? The prior over Z is Pi, means the ith element in the pi vector, and this is also very easy, the Gaussian distribution over Z, the mean is mu of Z, and the covariance matrix is sigma of Z. So I can put X inside this Gaussian, it gives me a number, multiply it with the pi I, and then I can get the summation over all possible Z, which is limited. For the case of our example, it is 25. So I can calculate the posterior over Z given X. It means that that black circle, I can set, this is just a notation. I have the conditional, I have the marginal, the unconditional, the probability density. All of them can be calculated easily for the case of the GMM, and this is the practical way you can calculate them. You put X inside this Gaussian, multiply this with pi r, and then summation of the all possible cases over the different cases of your categorical random variable. So let's think of this option. QZ equals P theta of Z given X. Sampling from the posterior given the observed data. What happened for the different categories if you know that you are at this point? What is the posterior? What is the posterior? What is the probability of each of these groups or categories given that you are at this point? Intuitively, the groups that are near to our point should have higher probability, and others should have lower probability. And you can see the same things here. All the categories in the far from your point are 0 almost, while the categories near your point are given high probability. Do you know why this 0.48 has the highest value in comparison, for example, to these other three categories? There are also three other categories which their mean is almost at the same distance to your observed point. Why this has the highest value and this has almost 0? Almost, yes. Yeah, exactly. It is because of the covariance matrix you estimate. For this, the covariance matrix is in this direction. It means that in the direction of your point, the covariance will decrease with a high rate. While for this category, you see that it is the covariance matrix intuitively. The covariance matrix is almost circular, so it can give high probability to your point. This is the problem, and it leads to the increased value in the denominator of the posterior you calculate, because your point is in the active region of the covariance matrix. It means that it gives high probability and the resulting posterior is higher. Okay, so let's start sampling. Instead of sampling with P theta of Z, which is uniform, all of them, the P theta of Z is a categorical over Z with vector pi, where this vector is 1 over 25 for all elements. It means that they are uniform. So if I replace this Q, this is our Q, which is the posterior. If I replace this Q and use the formulation we see, and use the formulation we have here, I want to calculate this summation. Okay, let's start again. But here I'm sampling from what? From the posterior. So you can see that here two of them are overlapped. You see the green is maybe one of, you can check. The blue and the green are overlapped, okay? I sampled 4 times again, and this time you can see that the groups and the categories near to your observed data are more probable to be selected. What is the higher the probability? These are the probabilities. And you know how to sample from a categorical distribution. In the first presentation, we have how to sample from a categorical distribution. You see that generally the samples, the selected, the sampled categories are those who has higher probabilities. These are the values. This is the value of the data density, and I write it here. Okay. This is another one, and you can see that both two of them, 3 of them overlap in the same point. Green, this color, and this color are the same here, and just the blue is here. So again, I write it here. This is another sampling. There are 4. All of them are 4. Because of the overlap, you can see them. You can't see them. And this is the last one. And look at these numbers. What happened? Yeah, the variance is much lower. So you can practically use it for sampling. Any problem? Is it clear? So, what happened? The prior was not a good option. Why? Because you have something to update your belief about how to sample Z. So, we have a framework named importance sampling that you can replace the sampling with respect to the prior with any Q, but you know that something is changed. When you are sampling with respect to the prior, you are calculating this expectation. When you are sampling from a Q, you are calculating this expectation. Both of them are easily calculated. You can easily calculate both of them. Just this is the difference. You sample Z, then you put it here, an average, and you sample Z here. You have Q, you have the denominator. The denominator is also the multiply this number with p theta of Z. Now I want to think of this expectation a bit more. This can be rewritten as this one. Okay, let's carefully take a look at these two expectations, this one and this one. What is happening? I update the distribution, and again, remember my figure that I talked about. This is the probability. This is your f function. You want something better than the probability. For example, this one. So, this procedure can be done using Q. And what is that correction factor? You know, I said that we should correct something so that I calculate this expectation. It means that the expectation of the blue curve with respect to this dashed one, and then go back to the original, because I do not want to calculate something else. I want to calculate the data density. Just I update the sampling so that I can trigger the function in the right place, in the place that the function has higher value. Okay? This is the correction factor. You know, this is exactly the same. This is exactly the term you are expecting, but here you have a correction factor. This correction factor retrieve the original value you are estimating. You are estimating this one. You cannot say that this data density is expectation of the blue curve with respect to both the black and the dashed one. No, this is not. This is exactly with respect to respect to the solid one, and this is the value. But when you want to make use importance sampling, you instead of sampling from the black, the solid curve, you sample from the dashed one here. And instead of calculating this value, you calculate the corrected value. But what is the important point of calculating with this formulation is that sampling from this Q, your values here are larger. You can see here. These are just factors differ with the condition. You know, just P of Z is the difference. Okay, so instead of sampling from the prior that give you almost zero in most of the cases here, you here sample from a QZ, and we see that the posterior is a good option, and the resulting P theta of X given Z for those posterior samples is large. Here we can see that. But you should correct it because you want to calculate the data density. And the data density is the expectation of the blue curve with respect to the solid curve. Just think of this factor as a correction factor. You know, this is exactly what you see in the importance sampling literature. Any question? Okay. So we have something new that we can use instead of the prior over z. We can use the posterior over z given x. Okay. But what is the problem? What is the new challenge? The posterior over z given x for GMM is easily, you can calculate it easily. But assume you are in the real world application where z is not a categorical random vector or random variable anymore. It is a continuous random variable, random vector. It is a Gaussian random vector. So to calculate the posterior over z given x, you should calculate the numerator and denominator here. And what's the problem with this? What?
The integral is interesting.
Yeah, exactly. The denominator is exactly the integral we are looking for. So the posterior is not tractable. This seems to be a bad option to select the posterior because it cannot be calculated. It is optimal. You will see that this is the optimal, this is the best distribution, but you cannot calculate what you want. And this is the next challenge we have. So, challenge number 2 was that estimating the likelihood using prior distribution while unbiased represents high variance. So the solution was importance sampling. We observe, we do not prove. We just observe that sampling with posterior for GMM can be a good option for GMM just. Because we see that the resulting estimate has low variance and it can be used for density estimation. But the new challenge is that the posterior over the latent, given the observed data, is not tractable in the general case. Because, again, it needs the data density. And data density is what we are looking for. Oh, here we start talking about the evidence lower bound. The evidence lower bound is a very great lower bound that brings some framework for you so that you can optimize Q such that it approaches the posterior without having a direct access to the posterior. You will see how nicely it do the optimization. Okay. So, based on the previous discussion, we have this expectation, and we need Q. Based on our discussion, we need this, the likelihood, the data density can be calculated using this distribution. But the most important point is that we do not need the density for training. We need the log density. You know, we want to maximize the likelihood, the log likelihood, or minimize the negative log likelihood. In either of them, you need the log likelihood or log of the density. So you need the log of an expectation. You need the log of an expectation. For 2 reasons that I mentioned here, just 2 reasons among other reasons, we are interested in changing the order of log and expectation. We see 2 reasons, but there are several reasons also. But the main 2 reasons we talk about here. So what are those 2 reasons? Okay? We know that we cannot trivially change the order because the log is not a linear function, so you cannot change it. If you have a linear function before the expectation, you can easily change them because most of them are linear operators. The first reason is that if I can change the order, it means that if I can calculate the expectation of the log instead of the log of expectation, then I can disentangle these two factors, I can convert the log ratio into the log of the difference of the logs, the log of numerator and denominator. So instead of one terms, I have two terms. So, okay? And we know that the optimization over the model parameters, theta, is just in the first term. And the second term is not dependent on your model parameters. It seems a bit interesting. The second term is not important for the model parameters, okay? But again, the second term, but again, for the Q, which we can see it as an optimization variable. Why? Because we want to design Q. We do not know what is the best Q. We see that in the case of GMM, posterior is a good option, but here we want to behave it as a variable, so we can change it to design Q. So, but Q is in both terms. It is a problem. Maybe you have Q here and you have Q here, but at least your model parameters is just in one term. The reason too is that if I know that I am in the practical world. It means that I want to estimate this expectation using Monte Carlo estimation. If I have the ratio of these two density, it means that first I should divide them and then average. So the uncertainty, because I am estimating, I am not in the exact form. I am estimating. For example, with 4 samples from the distribution, I calculate this ratio and then average. So if I have the log of expectation, which is the original one, I have the log of this summation, and the log of summation, I cannot do anything with the log of summation. If it was the multiplication, I can easily change it, but the summation is not working. So, but instead, if I have the expectation of the log, and again, I can have it in this case, then I have 2 different Monte Carlo estimation. It means that their signals, each of these have its own signals, which give you some intuition about the log likelihood. One approach is to samples, calculate the ratio, and then average. But in this case, first, the uncertainty will be increased by dividing them together. Okay? But here, you have no you have no ratio between these two properties. You have one of them is here, one of them is here, and each of them can provide you some intuition about the log likelihood. And it is preferable for us to have this form. But there are other reasons why we should use this approach, and we should change the order of log and expectation. Yes?
I'm not getting why dividing the 2 parameters is increasing the uncertainty instead of subtracting them.
Here you have just let's say we call it training signal. Each of the log likelihood, the objective of calculating the log likelihood is to update the parameters. In this case, first you are not in the exact board. You are in the estimation. You are in Monte Carlo estimation board. It means that you sample from 2 random variables to distribute. You sample from a distribution, calculate this ratio, and this ratio, each of them has its own variance, and when you divide them, uncertainty might be increased. In practice, you will see that how this affects the training of the autoencoders. But when I separate them, each of them sends its own signal, its own training signals to your model. This is preferable to separate them. It means that the expectation is now, for example, if one of them is selected in a good region, because you are sampling from the same distribution, but one of them may have a great signal. When you have the ratio first, that great signal may be hidden in the other one. But when you have separate them, that great signal has its own role, and the other signal has its own role, and maybe the first one update your parameters better.
So you use the first term on the subtract equation for training the model parameters, and the right one for finding the Q.
The right one and the both of them are used for
Q.
Yeah.
Yes.
And it is a very challenging problem because Q is a parameter of the sampling distribution, as you said in the previous session. Q is a parameter of the sampling distribution. It's a very complicated problem. We see that how we can solve it. Okay, so for two reasons, we are interested in changing the order of log and expectation. We have the log of expectation, but we want the expectation of the log. Why? Because the expectation of log can separate those two distributions, okay? But the point is that we know that equality is not the option, but which of these other signs should be used here? This is important, okay? We have one inequality, Jensen's inequality, that states that assume a random variable x and a concave function phi, the concave function psi, then the psi of expectation is greater or equal to the expectation of the psi. What does it state? Assume that the function is log, which is concave. The log is concave, as we know. It is concave. Okay? We have a concave function, we have a random variable z. So what happened? Which of these can be selected? You are exactly the same as what you see here. Log this function expectation over a random. This can be any function, not random variable itself. Maybe I should remember it here. Okay? It can be any function of the random variable, not random variable itself. So the log of expectation is greater or equal to the expectation of the log based on the Jensen inequality. So we can select this sign here, and it means that what we want, what we have, and what we are interested to have, what we have is greater than what we are interested to have. It means that the log likelihood, which is the left side, is greater or equal to the expectation of the log. And this is what we call evidence lower bound. This is a lower bound to the log likelihood. Changing the order, make it a lower bound. Is it clear? Okay. So the log of the likelihood is the log of this expectation, and based on the Jensen inequality, we know that we can change the log and expectation, while instead of the equality, we have greater or equal sign here. So the log of the log likelihood is greater than the expectation of the log of this ratio. So by changing the order of the function and expectation, we have a lower bound for the log likelihood known as evidence lower bound, or abbreviatedly ELBO. ELBO is a very well-known value in the variational learning literature. You understand how ELBO was created? We have the log of likelihood. We want the log of likelihood. Why? Because we want to learn the model, to train the model, and after that we want to estimate the density for new random variable or new instances. It means that we want, for example, we want to have the OOD, out of distribution detection. So you need to calculate the likelihood. But we see that in the likelihood, we have the expectation of the log. For two reasons that we talk about, we need to change the order of expectation, the logarithm and the expectation. But we do not know what happened to what is the log likelihood and what is it after changing the order. Jensen inequality says that by changing the order, the right side is lower or equal to the left side. And so we have a lower bound on the evidence. Okay, so let's have a notation here. We will talk about this concept more and more during the next two sessions to fully understand what is happening when you are using ELBO. So you have the log likelihood. This log likelihood is expectation with respect to z coming from Q of z of the joint of your model over the sampling distribution. Okay? This is what we have. The log of this expectation. We see that by using the Jensen, you can change the order. So this lower bound is a function of two, let's say, parameter. One of the parameter is the model parameter. The other parameter is this Q. It is not a parameter, we know, it's a function. But now assume that it's something that we can tune. For example, like parameter. The parameter can also be tuned using optimization. This Q, assume that can also be tuned using some types of optimization. Everything you are talking about is about the data points. But these are different. It is the data point. These are parameters. So I separate them with a semicolon. And call it the ELBO. So why I have this notation? I want to emphasize that everything I'm talking about is in one point, just one data point, nothing anymore, okay? And there are two things that play an important role in this ELBO and can be changed to change the ELBO. The model parameter and the data distribution you are sampling from. Clear? So I have this notation, ELBO of x, theta, and q, which is the expectation of the log. We know that the expectation is with respect to the sample coming from q. The log is the log. The log of the ratio is the log of the denominator minus the log of the denominator. Okay? So this is ELBO, it is nothing more, but we have one important point here. If you we change the order so that we can convert the ratio to the log of ratio to the log of nominator minus the log of denominator. So we have these two terms for the ELBO, and one important point is that this term shows an information theoretic property of your distribution, which is the entropy of the distribution. Then the entropy is exactly, you can see the definition here, minus the expectation of the log of the probability that distribution assigned to random vectors. It is not very important for us, but in some information theoretic based approaches, they start from this point and work on this definition. But here we just, I just want to notify that this is the entropy. Some of you may be familiar with the entropy definition. Okay. So what happened? I am not interested in maximizing the ELBO. I'm interested in maximizing the log likelihood for training. Okay, so but there is interesting relation between ELBO and your log likelihood. If you have, for example, this log ELBO, you know that the log likelihood, you are certain that the log likelihood is above ELBO, because ELBO is a lower bound to the log likelihood, okay? For example, this is the log likelihood. If you maximize the ELBO, it means that you are hopefully maximizing the likelihood at the same time. It's clear, you are maximizing the lower bound, so you are maximizing the log likelihood, which is which we are certain that is higher than the lower bound. Okay? So we replace the maximization of the log likelihood with the maximization of the ELBO. Why? Because of the relation between ELBO and the log likelihood. It is a lower bound. You push the lower bound upper and upper. It means that you are you are hopefully. We see that sometimes it is not, because it is a lower bound, and we do not have any information about the behavior of this lower bound. It is just a lower bound. If you push it upper and upper, it means that the likelihood is also increasing, hopefully. But in practice, you will see that variational autoencoders can be trained, so it works. Okay, it works. But there is an important point. How tight is this lower bound? Are they matched, or there is a distance? How much is this distance? If we can characterize this distance, it would be very great. You have also some information about how tight is the distance. Okay? Let's talk about the distance between these two values. Any question? Okay. If you write down the KL divergence between the Q distribution and the conditional distribution of latent given observed data for your model, we know that this was a great option to be considered as Q. But we do not have access to this value, so we cannot select it. So just assume that there is a functional form for the posterior, and I want to use it here. The KL divergence says that the KL divergence between two distributions is the expectation of the log of the ratio of those distributions with respect to the first distribution. I write it here again. So I can replace the conditional distribution of latent given observed data with the joint or the marginal distribution of your observed data. This is just the application of the Bayes rule. So the log of these three terms is the log of p theta, because it is in the denominator, is a denominator of denominator. It means that it is a numerator. You have the log of p theta, you have the log of the joint, and you have the log of q. Clear, yes? The expectation of these three terms. So, for the first one, I have, assume the first one, I have the integral over z, qz times log of p theta of x dz. What does it mean? I can put it outside the integral. Why? Because it is not dependent on the latent. Okay? And the integral of qz dz, the integral of qz dz is 1. Because you are integrating over the whole domain of a PDF. And we know that each PDF, this integral for each PDF is equal to 1. The area under curve. Yes? The area under curve is equal to 1. So you have log of p theta of x times this value minus the qz, the joint. Oh, there's a problem here. This is the log of joint, you know, log of joint here, and this is the log of qz. Can you observe something interesting here? There is a very interesting point in these three terms. The first term, this integral is equal to 1. So it is log of the log likelihood. The first term is log likelihood. The second and third term remind you something.
Here.
What?
ELBO.
Yeah, these two terms are minus ELBO. The first is the log likelihood. These two together, the minus, factor the minus. These two together are ELBO. What happened? We calculated tightness metric. What we have on the right before. What we have, the ELBO. The ELBO is a lower bound to the likelihood, the log likelihood. The difference is the KL divergence between the Q and the posterior. Is it intuitive? How much is the distance between the Q and the posterior? The model posterior means that how tight is the ELBO. And when you have the tightest ELBO,
And Q and the posterior.
yeah, exactly. You have the tightest ELBO when Q equals the posterior. It is very intuitive. No, don't worry. You know, in the case of GMM, you see that when using posterior in the GMM, when we use posterior, we have a very low variance estimation for the likelihood. You remember? He will talk about this idea more and more during the next two sessions, but just have an intuition that you want to calculate the log likelihood. ELBO is a lower bound. And the distance between these two is the KL divergence between the Q and the posterior, the model posterior. It means that if you select a better Q, you have a better lower bound. And if you have, in the best case, if you have Q equals to the posterior, it means that they touches each other in that point, because the difference is 0. Q is posterior, okay? ELBO in that point, this is ELBO. This is the model your current model, it means that your theta. Just at this point, these two touches each other. And if you increase the ELBO, this is not the case. For example, this is the likelihood, and this is the ELBO. If you increase the ELBO, you are certain that for small steps, you are certain that you are increasing the likelihood, because in this point they touch each other. So the direction for this point is exactly the ascending direction for the data likelihood. We will talk about this concept more and more and more. Do not worry. It may seem complicated, but it is very nice tool used in different probabilistic approaches. Thank you very much. If you have any questions, we can talk about.